Sorry for being very loud. So thanks for having me again. This is an update on where we were since last EuFMD meeting, where we had initially begun to essentially field validate some of the molecular-based technologies that we have available to us. I should say that a large proportion of this presentation that I'm going to give you now has been done by my PhD student. Oops, hang on. Where's the pointer? Here, who is Emma, who you can see here. And when I looked at the programme, I did slightly worry in that this appears to be one of the only presentations with relation to field-based diagnostics. And I'm kind of hoping that's not because people have given up, because hopefully you will see today that actually it's a very promising stream of work to continue. But I do hope that it's because at Pirbright we are leaders rather than that nobody is interested in this work. So those of you that know me that as this is my life's problem at the moment. It's how do we enable better pen-side diagnostics to be able to help us in the field with to confirm local clinical observations. Because as we know at the moment, they're challenging. FMD, for example, is a disease for which other diseases can present. And as you can see here, oh, I keep doing that, I'm very sorry. This is an example of where we might be visiting a farm, but we couldn't say for sure whether this was foot and mouth disease or swine vesicular disease. And over here, we couldn't say for sure whether this was foot and mouth or vesicular stomatitis. So we need better tools to be able to enable us in the field to be more efficient with the way that we draw conclusions. Because if we don't do that, the potential impact and the potential size of an epidemic can be compromised. And you will have all seen this before, but that was illustrated in one of the reports that came out following the 2001 outbreak of foot and mouth disease in the UK. So there has been a massive boom of publications in the field of diagnostics that could be transferred to field settings. I've just illustrated them here with regards to those where you might take real-time PCR and you develop platforms where you can basically do extraction and real-time PCR in the field. But more recently to that have been these isothermal technologies such as LAMP, which you've heard me talk about before, and other technologies such as RPA, which is a similar technique. But with LAMP and RPA, we can also simplify that further by running those types of tests in water baths with very simple visualization techniques such as lateral flow devices. So at the moment, there is around about 17 isothermal publications, and that kind of illustrates how everybody got a little bit carried away with, oh, LAMP is brilliant, it's very simple, we can perform it in the field using very basic technologies. And there was this huge boom in publications, not only for foot and mouth, because these are specific to foot and mouth, but for other pathogens that we're familiar with. And with regards to PCR, there are currently, or there was at the time of writing this presentation, 5 real-time PCR publications that have been validated on portable platforms. So that's to kind of give you an idea that there's lots of publications out there, but my main problem with this is that they're standalone publications. So when you look at an individual publication, it's very nice. It's been quite often, if not, well, in most cases, it's been compared to what we might consider a gold standard, whether that's virus isolation or real-time PCR. But the main problem with it is that it's a standalone publication in that it's not compared against other technologies and other platforms that are existing out there. So we are in a situation where we can't really fully understand what is our best field-based option at the moment in terms of molecular-based technologies. So the aim of what we've been doing quite recently is to take a selection of platforms and the assays that are performed on those platforms and to run them alongside each other to actually get a real understanding of how they perform against each other in comparison to gold standards. So in that respect, sorry, I keep doing that. In that respect, so this is our gold standard. We didn't use virus isolation. We consider the diagnostic real-time PCR, which is the Callahan assay that everybody is familiar with. We consider that as the technology to benchmark against. And we selected a portable real-time PCR machine You've heard me talk about these before, I'm sure, but as things move on, the platforms that we have evaluated in the past have become obsolete, because as times are changing and as medical science moves on, there are better platforms that become available. So this is a Tetracore 8 machine. It's produced by Tetracore. It's a T-Core 8, I should say. It runs on lyophilized reagents. The lyophilized reagents are a take on Callahan, but they are slightly modified. The protocol is essentially a modified Shaw protocol, which all of you will probably be using anyway. But the key difference is there's a slightly reduced RT step, which is common to the work that we do because it enables us to be able to perform molecular-based technologies quickly in the field. So we want a test when we're using real-time PCR that's less than an hour, and you can easily shorten your RT step with absolutely no effect on the performance of your assay. And then we had two isothermal assays. So we had what you've heard me talk about before, which is the portable RT LAMP assay. This is a Genie 2 machine. It allows you to do LAMP in real time, which is obviously not entirely necessary, but we like to do it as part of our research so we can see things happening in real time. This portable RPA assay. So the key difference between LAMP and RPA is that although they're both isothermal methods in that you're running them at a single temperature, which is different to PCR, where you're running at multiple temperatures, RPA is run at a lower temperature, so it's 42 degrees instead of 65 degrees, and it's a shorter assay, in that you would expect to get a positive in less than 5 minutes, whereas LAMP, generally speaking, we get positives within about 10 minutes. So when we compare those assays all together on exactly the same template material, this is an RNA standard copy number along the top here, using a decimal dilution series in carrier RNA, you can see that LAMP, as we have reported before, has a similar analytical sensitivity to real-time PCR. And that is also the case for the portable RT-PCR machine that I'm going to show you the results for in a minute. But the analytical sensitivity for RPA is 1 log less. And that was quite nice for me to see that, because there's obviously a lot of publications out there on RPA, and you think, well, actually, this might have advantages over LAMP, for example. But clearly, the reason that nobody's using RPA is this effect on analytical sensitivity. So it was nice to see that benchmarked against all the other tests that we've evaluated. So with regards to diagnostic sensitivity, the T-Core 8 platform, which is the portable real-time PCR machine, had 100% concordance. And actually, this machine will detect CTs up to 45 cycles, which is very good. The RT LAMP had 88% concordance, and the main reason why there is a reduction in the concordance of RT LAMP is that the CT at which it detects up to is 30. So really those late samples, the late amplification, LAMP will not detect. So it's a very good technology for confirming positives, but you would question whether you would use it for detection of negative samples. The LFD is very similar, so essentially there's no difference in this test other than we are visualizing the products using a lateral flow device, so we're not looking at them in real time. So the only reason there is difference there is because in order for you to be able to see it on a lateral flow device, you need a certain number of labeled products. And although you can see them here, because of intercalating dye, it does have a slight reduction effect when you're visualizing by a lateral flow device, just because you need enough product. Whereas RPA performed very poorly. It only had 77% concordance and only detecting up to samples with a value of less than 27. So one of the things that I should have said a minute ago is that the ultimate aim of this is to basically find out which is the best 2 platforms that we have currently available to us for field testing, and to take these platforms to endemic settings for evaluation. And in order to do that, we wanted to make sure that our sample processing was also evaluated. And those of you who have heard me speak before know that we don't do extraction. So for field-based settings, we move away from extraction, and we do very simple dilution strategies. So this is just an example for epithelium and all 3 of the technologies down here. So you have RPA, LAMP, the T-Core 8 against the gold standard here. And this is if you were to do it in a laboratory. This is if you were to do it using an extraction kit that's manual, because you could do that in the field if you wanted to. But this is our most favourite option, which is basically to dilute your sample in water. And the take-home message from this particular slide, as it is for the next two, is that LAMP and the TCOR 8 are really the ideal samples, ideal platforms. But actually, if I was to be totally fair, the one that comes out the best is the real-time PCR performed on a portable platform. So this is epithelium. All we do is to take the epithelium out the mouth, grind it up, and then put it straight into the assay at one of those 3 dilutions. Serum is slightly more complicated because you do have to spin to get the serum. But we can do it. We get the same picture in that LAMP is a good option. RPA is very poor, but the portable PCR outperforms LAMP. And it's the same for OP fluid, which is your probang samples. So what we did at this stage is we dropped RPA. So I would recommend to you that if you're considering using RPA assays, it might not be the best option, and perhaps that's why people don't actually use them. So we took LAMP and the portable real-time PCR to endemic settings. The last time you heard me speak, we had done most of our evaluation in Tanzania, but we've now extended that to another location in Tanzania, which is in northern Tanzania in the Serengeti, and that's in collaboration with the University of Glasgow, and also Kenya, facilitated by EuFMD. And so this is us performing LAMP in the field on a range of clinical samples. So we have epithelium, serum, and probang samples. And you can see quite nicely that we can perform it on a range. So depending on the lesion age or the clinical stage of the animal, we can reliably detect positives, quite straightforward by RT-LAMP. And when we compare that in a laboratory setting, in endemic settings, so if we take those samples and we then run them on a benchtop real-time PCR machine, we have a very nice correlation between our LAMP results and what we would get if we were to perform a conventional type of real-time PCR in a laboratory setting. But just remember, for LAMP, it's a brilliant tool for confirming positives, but up to the point of around about a CT of 30. So those later positives or negative or early stage preclinical, it might not be the best tool. So the TCOR 8, this is brand new data. This hasn't been presented before. It's in preparation for publication. We have taken this to a range of different settings, also including Ethiopia. So we have done Kenya, Tanzania, and Ethiopia with this piece of equipment. We have extended to lesion swabs, which was a really nice presentation earlier that we listened to, in that lesion swabs are really quite a nice sample to be using. They're simple to collect. The actual lesion age at which you can collect the sample and still detect positives is beyond that of something like serum, for example. And even epithelium, when you start to drop off with your positives for epithelial samples, we are still picking up positives using lesion swabs. So that's really quite a nice observation that we've made quite recently, in that even lesions of 7 days old, if we swab the mouth, we can still detect positives. But this is all well and good. We all know that that's probably foot and mouth in the animal's mouth. It's nice to be able to confirm it quickly using a technology that is probably, people would believe you more than if you were using LAMP. But what we've continued to move on to now is actually serotyping in the field. So in-situ serotyping. But before we did that, we just wanted to check that we obtained the same correlation between the TCOR 8 results that were generated in the field and also running them on a real-time PCR platform in endemic settings. So we get this nice correlation. So that gave us a really, really good confidence that this test is performing well without extraction. So this obviously combines an extraction. And the results that we are getting are consistent if we were performing this test using conventional techniques. So this is absolutely brand new data. This is us in the field.
1 minute, please.
This is the last slide. This is us performing serotyping in the field using a test that was developed by Kasha at Pirbright for East Africa. strains of foot and mouth disease. And in all samples that we have analysed, including probangs, lesion swabs, epithelium and serum, we are able to, within an hour, serotype them without extraction in field settings. So just to quickly touch on LFDs, just to wind everyone up again. These were 20 LFDs from Tanzania that Tiziana Lembo had collected along with various other people at Nelson Mandela in the northern Serengeti region. They were shipped to Pirbright, and we used the serotyping real-time PCR assay on them, and we did next-generation sequencing. And what was very nice is that in continuation to work that we had done previously, we were able to serotype very nicely these samples 2 years after they were initially used in the field. So they had sat at room temperature on a shelf in a cardboard box for 2 years. We were able to process them at Pirbright to not only confirm serotype, but actually show relationships between farms, as you can see here in phylogenetically representative, and also to detect different serotype outbreaks less than a month apart on the same farm. So this is why I was quite anxious to continue the work with LFDs, but to consider these are real clinical samples as opposed to virus isolates. So to finish, the analytical sensitivity of the portable platforms that we have at the moment is the best for portable real-time PCR. We do this without RNA extraction, and we can now serotype in situ on the farm to basically not only confirm that it's foot and mouth, but to actually in real time tell us what serotype that is, to enable us to have more tools essentially available for decision making. So bringing it all together, Pirbright and our colleagues at Glasgow will be taking this forward, hopefully, in a GCRF application, whereby we will be using lateral flow devices, which Tiziana mentioned in her talk the other day, at a community-led level. So you'll be using these for farmers to basically collect the sample themselves, and then we will be processing them for molecular-based epidemiology, with the idea that the use of the lateral flow device actually preserves the sample. So we should not see degradation in the sample that we see currently with samples submitted to Pirbright. And that is all I have to say today. And I have to thank a lot of people, including the Maasai. So there we are.
Thank you, Veronica, for this presentation. I don't know, Nadia, the next speaker, I hope it's ready to, so we can take one quick question because we have somebody online for the next presentation. Any question? No? So thank you, Veronica. Thank you very much.
Okay.